So hi there, in this clip we are going to just do some basic notation that we are going to use for principal component analysis. So we will represent our training examples as basically column vectors. We are representing vectors as column vectors, and so every training example xi would be, it has D features, capital D number of features, let's say, and we call these feature vectors also. So xi1 is the first dimension, xi2 is the second dimension, and so on up till the dth dimension. And all these are the D dimensions of vector, the ith training example. And if we want to represent the entire data in the training set, then we could do it using a matrix in the following way. So you would represent every training example as a row, and you know that every training example has D dimensions, and every row is a different training example, and you have m number of examples. So m number of examples, right? So alternatively, you could write this as x1 transpose. So you know that x1 is a column vector and the transpose would be a row vector, right? So this is x1 transpose, just a concise notation. And every vector you could represent it similarly. So you have a row-wise representation of x. And if you take the transpose of x, x transpose, then these row vectors become column vectors. So these dashes here, the horizontal dashes indicate that they are rows, and the vertical dashes indicate that they are columns. Also, you have to bear in mind that in the case of principal component analysis, we assume that all training examples are normalized by subtracting the mean and dividing by the standard deviation for each feature. Okay, so what are we going to do? For every value, for example, for xi1, you would subtract out the mean for feature 1 and you would divide by the standard deviation of feature 1, right? So meaning if you have a feature j, so for the first example you would basically do x1j and you would subtract out the mean for feature day j and you divide by the standard deviation for feature j. So when you do this for all the entire data set, for every feature and for every training example, when you do it, you will find that the mean for all features becomes 0, meaning mean for all dimensions becomes 0, and the standard deviation for all the features or dimensions becomes 1. Next, we just want to develop some kind of concise notation that's going to help us in our principal component analysis. We want to write a simple way for representing covariance of two features, right? So let us say that feature number I, which means that all the numbers x something I, right? Meaning that the ith feature for across all the examples. and let's say that corresponds to feature I, and let's call it as capital Fi. So capital Fi is a random variable representing the value of the ith feature. Okay, and similarly you could write for Fj the jth feature, and you could compute the covariance of feature I and feature j, and by definition that would be equal to expectation of Fi minus mu I into Fj minus mu j. And frequently we replace the covariance by the sample covariance by computing from the data. So we would take every example, and this is the kth example. For the kth example, the ith feature, and subtract out the mean of the ith feature. And for the kth example, jth feature, and you subtract out the mean of the jth feature, right? And then you find out this product, and you sum over from one over all the examples and divide by the number of examples. And if it happens that mu I and mu j are 0, because which happens in our case because we are subtracting out the means in the beginning itself, so we would find that the means are 0. And when you do that, you just get this expression summation k equal to 1 to m xki xkj, and divided by m. Now let us represent the ith feature as Fi. It's by a vector representation. So Fi will be the ith feature value across all the examples, and we can write that as ith feature in first example, ith feature in second example, and so on up till the mth example, and similarly for the jth feature. Okay, so when we do that, then we would realize that this expression here, which is the covariance of Fi Fj, and then that would be just 1 by m, and it would be the dot product of these two features, these two vectors. So the k covariance would be just the dot product of these two vectors. And this is a concise representation for the covariance of between feature I and feature j. Next, let us develop a concise notation for the covariance matrix. So the covariance matrix just reflects the covariance between every pair of features in the data. So the ijth entry of the covariance matrix, let's say this one, this is the second row and the second column. So this would be just the covariance between feature I and itself, right? So that would be just its variance, right? So covariance between feature I and feature I is just the variance of the feature I. And let's take that one. So this is the covariance between the second feature and the dth feature, last feature. So that is just the summation of xi2 minus mu2 xid minus mu d, and divide by 1 by m. And all the this is by definition of covariance, but that all the means are 0 because all our features have been normalized. So all the means are 0. So we are assuming all the means are 0. And we just developed a simple notation for the covariance between two features. So we could write this in the form below here. So for example, this one would be F2 transpose Fd. Okay, and 1 by m of that. So we get this entire matrix. And note from this matrix, the first row, the left hand side is always F1 transpose, and every row, the second right hand side is the same, right? Oh, I'm sorry, every row, the left hand side is the same, you see? And in every column, the right hand side is the same. So we could represent this in a more concise form. This is just the same as, I factor out the 1 by m because it's common to all the terms. It's common to all the entries. And then the rest can be written in this concise form. F1 transpose, F2 transpose, FD transpose, and F1, F2 up till FD. Okay. So F1 transpose F1, that's the first entry. F1 transpose F2, that's the second entry. F1 transpose FD, and that's this entry. And basically for all the other entries. And now note that F1 transpose is the feature values for the first feature across all the examples, and F2 is just the feature value for the second feature across all the examples. So when I stack these up vertically, these features, then the columns will correspond to each example. Okay, and so I can write these two in a more concise notation. This is nothing but capital X transpose, and this is nothing but capital X. So the covariance matrix sigma can be written in a concise form as 1 by m x transpose x. So this is the end of our clip on just the notation for principal component analysis. Thank you very much.